Yeah, there, folks. This is just the video, like I say, I was going to post running through our higher paper mock. Now, we've already been through a bit of this paper, so what I'm going to do is I'm going to just sort of skip over the first few questions. If you desperately do want to go over them, on the foundation video that I've uploaded, these questions are actually covered a bit later on. So when I'm going over questions 6, 7 and 8, I think this is actually question 7 on the foundation paper, and this is question 8. Now, we did go over that in lesson. If you want to look over how to do those questions, I would go back and have a look at the end of the foundation video. Okay, so we're going to start off from question 3, and what we're going to do is we're going to go through, talk about what kind of the topic the question is about, have a look at how we'd answer the question, and maybe have a talk about some of the trickier ones and how to avoid any pitfalls there. So let's make a start, and the first one, bit of an awkward question to get us started. It says, what is the approximate radius of an atom? Now, we've not covered this for ages, okay? The radius of an atom is usually measured in what we call an angstrom, which is a times 10 to the minus 10. Now, I've deliberately put this as one of the first questions on here because this hasn't come up for a few years, and I have a feeling they may ask this again. So just remember, the approximate radius of an atom, I mean, it makes sense if you think about it, because it's certainly not going to be 10 meters. It's certainly not going to be, what would be 10 decimeters there, sorry. And this would be quite small, but not that small. Sorry, this would be extremely small. Okay, this would be on the subatomic level. I thought it was a fifth option for some reason. So, figure 4 says, here we've got, obviously these aren't the actual elements, some atoms, and it says, complete the sentence. All the elements in figure 3 are in group something of the periodic table. So this is where your periodic table is going to be handy. So if you had a periodic table and you could look at it, ignoring the letters, you can try and find the ones here that have the same numbers. So if you have a look on your table, okay, you can see we're talking about a group. So obviously going up and down. And if we look at the various amounts that we've got here, we can even have a little toy around with it. What you can see, this one's got 3 electrons, 11 electrons, 19 electrons. So if you actually try just drawing any of those out, so 2 and then 1, or this one here, 2 and then 8 and then 1, or 19 would be 2, 8, 8 and 1. They've all got 1 electron on their outer shell, which tells you it's in group 1. So you don't have to draw those models out. You can do that in your head. You can even just look at the numbers and you'll notice that this matches up with sodium, this matches up with lithium, this matches up with potassium, and so on and so forth. But there's a couple of different ways of cracking that nut there. Moving on. Which 2 atoms in figure 4 are isotopes of the same element? Well, I think this is quite nice and easy. So the first thing to do is to identify what an isotope is. Okay, and we've not done isotopes for ages. So isotopes are elements with the same number of protons but a different number of neutrons. And that will actually get me 2 marks, even if I've not said which atoms yet. So isotopes are elements with the same number of protons and a different number of neutrons. 1 mark for each underlined bit there. Now, looking back at the data, if you know your mass number and your atomic number, well, the atomic number is the number of protons, and the mass number is the number of neutrons. So looking quickly at this one, we do a quick little bit of penning. So this has got 3 electrons, 3 protons, 4 neutrons. This one here, next to it, has got 3 electrons, 3 protons. Sorry, I'm getting them wrong bloody way around. That one's got 3 of each. That one's got 4 neutrons. So you can see here clearly R and S must be isotopes of each other. So that's what I'd add there. So R and S are isotopes. And that's how I get my 3rd mark. So question 3.4 is actually a 6-marker question on the reactivity of the halogens. Okay, and what it wants us to do, it wants us to, let's read, explain the trend in the reactivity of the halogens. So clearly, if we're talking about a trend and we're explaining it, we need to say what the trend is first, and then we need to say why that trend happens. Okay, so where I would start with this is I would say that group 7 elements become less reactive down the group. Okay, that is the trend. Okay, and I'm definitely going to get a mark for popping that on there. So we've said what the trend is. The group 7 elements become less reactive as they go down the group. Now we need to explain why that is. Okay, so simple starting point is to say what group 7 elements are and what they want to do. So group 7 elements have 7 electrons in their outer shell. Which means they want to gain 1 electron to become a -1 ion with a full outer shell. I'm leaving no stone unturned with my answer here. Okay, so the way that the mark scheme for this works, and you can look at this for yourself on the way that I post, is they'll give you what's called a bunch of levels. So it'll talk about a level for your answer, whether it's level 3, 2 or 1. All that basically means is a level 3 answer, you'll have made most of the points in the mark scheme and you'll have logically linked them together. A level 2 answer, you'll have mentioned some of those points and mostly logically linked them together. A level 1 answer, which will only get 1 or 2 marks, you've just made a few simple statements and you've not really kind of linked them together. So on a 6-mark question, this is why I always say, write down a load of random crap. If you're doing this question, you've left it till the end and you come back to it and you don't know a blooming thing about how to answer it, just tell me some facts about group 7 elements. You might get a mark or 2 at the very least. So we've now said what they want to do. Group 7 elements have 7 electrons in their outer shell, so they want to gain 1 electron to become a -1 ion. Okay, and what we can say now, you'd even do a little diagram to help explain it. Okay, so if we had something like fluorine, okay, versus something like bromine. Okay, you can see fluorine has got 2 shells, but bromine's got 3 shells. So if what they want to do is to attract an electron in, okay, well, what that means is the one with more shells is going to find it harder to attract than the one with less shells. So that's what we need to talk about here. So halogens further down the group have more shells. And what that means is it makes it harder for them to attract electrons because there's less attractive force. So to kind of bring it all together, so as we go down the group, they find it harder to attract electrons and so are less reactive. So if I was presented with that answer, I'd be quite happy with that as an examiner because it makes my life a lot easier than some answers you'll get. So I can see they've clearly explained the trend. They've said what group 7 elements are and what they want to do, okay, for 2 marks. They've then said they've sort of explained the trend, linked it to the electronic structure, and then linked it back to the original idea of reactivity. So that I would say is a very good answer, if I don't mind tooting my own horn. But as you can see, I have used sentences but I've split it up into bullet points. You do not need to write a massive long flowing sentence. If you want to break it up or you want to use diagrams, go for it. There's nothing that says you can't. Okay, moving on to is it question 4 now? Yeah, question 4. So question 4 is a electrolysis question, as you can probably work out from the fact that it says the word electrolysis pretty much straight away. So question 4 says copper can be produced from copper 2 sulfate solution by 2 different methods. And method 1 is electrolysis. So what they want you to do here is they want you to draw a setup to produce copper from copper sulfate solution via electrolysis. Now this is nice and easy. You just need to draw an electrolytic cell. So you should have a beaker, you need your electrodes, okay, and oh right, yes, sorry, we need the DC power supply. It says there's a switch as well, apparently. So I'll just connect a switch up here. And other than that, now all we need is my actual copper sulfate, which is in here, and we need to label it. So there's my copper 2 sulfate. There's my electrodes. I'm going to label them properly, but you could just put them as an electrode if you weren't sure. So there's the anode and there's the cathode. Remember not to panic. Positive anode, negative is cathode. So in terms of this, the mark scheme says electrodes connected to DC power supply by wires. So there's the electrodes. They must be dipped into a solution, and then they want you to have labelled the electrodes. So I think that's a bit mean because they don't actually specifically say there, label the electrodes, but you do. Okay, so it's very much worth knowing your anode and your cathode. And question 4.2 is very much an application question. So it says, let's say we turn this on. The copper 2 sulfate is very blue, okay, as you'll know because we made it. But when you turn this on and the power pack's running, what's going to happen is the colour of this solution is going to change. It's going to fade from blue and it'll probably become more of like a grey colour. And it wants you to know why. Well, what's happening is it's the copper ions that cause the blue colour. Okay, transition metal ions like copper ions are generally brightly coloured. And what's going to happen, and that's our first mark, is that when we turn that power pack on, the copper ions which are in this solution, they're going to go to the negative cathode where they're going to gain electrons. Obviously you don't need to do this in your answer yet, but this is what's happening. So that's going to turn them into copper, and copper is going to build up on that electrode there. So what we can say here is that when the power pack's turned on, the copper ions are going to be converted to copper metal or copper atoms. So the number of copper ions goes down, what that means is it gets less blue, okay, because the copper ions cause the blue. So I thought that's quite a mean question, okay, which is why I popped it, or why I picked this one. I think it gets a bit meaner before we're done though. Okay, so now we've said classic 4-mark question on electrolysis. It wants to know how we work out how to produce copper 2 sulfate, sorry, how to produce copper rather, from copper 2 sulfate. So we can do this in bullet points. It does not need to be massively, over the top. So we've sort of talked a bit about this on the last one. So the copper ions are going to be positive because metals always form positive ions. So that's where I would start. I would say that the copper ions are positive, so are attracted to the negative electrode, aka the cathode. And there's actually 2 marks there. So firstly I've said the copper ions are positive, and I've said where they're going. So that actually gets me 2 of my marks there. Sorry folks, the camera's in a bit of an awkward position. And then we've got the next couple of marks. So we need to say what happens to those copper ions. Well, the copper ions will gain electrons and be reduced to form copper ions. Now, I don't need to actually include this equation, but this equation is just useful to think about what's happening. So the copper aqueous in solution is going to gain 2 electrons and it's going to become solid copper, and obviously that's going to mean that we're going to produce copper from the copper sulfate solution. So not a nice question. The next question is not very nice either. This question 4 is genuinely quite a difficult one. So let's look at method 2. So this is a displacement reaction. So it says the chemical equation for the displacement of copper using iron is CuSO4 plus Fe goes to Cu plus FeSO4, and it wants us to calculate the minimum mass of iron needed to displace all of the copper from 50 centimeters cubed of iron sulfate solution. So this is quite a tricky question, and we'll go through obviously the working out for that in a moment. I just want to check, I can't quite remember. Yeah, that is the last bit of question 4. Right, so what are we doing here? It's 4 marks, as clearly there's a lot of calculation going on. Well, there's a few different ways we could approach this, but the first thing we need to do, we've been told we need to find the minimum mass of iron. Okay, and what that should tell you, any question that says minimum mass, is that this is a reacting masses question. This is a reacting masses question with, I say, a little bit of a twist, just a slight twist on it. So we've been told that we've got 50 centimeters cubed of copper sulfate solution, and we've been told that the concentration of the solution is 80 grams per decimeter cubed. So the first thing that I would do here is I would work out the RFM of copper sulfate. Okay, now if you add it up together, copper plus 1 lot of sulfur plus 4 lots of oxygen, you're going to get 159.5, and that is going to be your first mark. Okay, and it might be an idea as well, just to jot down your moles triangles, because you never know when you might need them. So now that we've got that RFM, what we've got to try and do now is we've got to work out really how much of the copper sulfate that we've got. Oh, just give me 1 second, folks. I think someone's going to pop into the room. Sorry about that, folks. Just had someone pop into the room then. So what we'll do, where's my piece of paper gone? We'll pick back up with this question, which is a bit of a sort of combination of reacting masses and something else. I just want to get a scrap of paper. I'm just going to scribble on the page by accident. Moment. There we go. So when we left it, oh sorry, I wound up, someone asked me to jot something down and I wound up putting it over the blooming working. So we said the RFM is of CuSO4 is 159.5, okay, and that's just going to get us a mark because we're going to need that. What we need to do next is, we were told in the question that 80 centimeters cubed, as you can see, where is it? There we go. 80, sorry, not 80 centimeters cubed. We've got 80 grams per decimeter cubed, okay? And we've been asked to find the amount in 50 centimeters cubed of solution. So a decimeter cubed is 1,000 centimeters cubed. It's the same way as saying that. We've got 80 grams per 1,000 centimeters cubed. So if we're doing 50 centimeters cubed, we need to reduce both sides by the same amount. So what I would do here, I would do 1,000 over 50, which is going to give you 20, and then I would divide the 80 grams by the 20 to tell us that it's 4. So what we can say is that there is 4 grams of CuSO4 in 50 centimeters cubed of our solution. Okay, so that is going to be another mark for us right there, and that's the kind of weird bit. Beyond this, it becomes quite straightforward. So what we've got to do now, if we look back at the equation, you can see it's a fairly straightforward equation. It's a 1-to-1 ratio, so we've got our copper sulfate and our iron. So we now know pretty much everything we need to know apart from the moles. So what we've got to do, we've got to take our mass, okay, remember the moles triangle mass, MR. So we take our mass, which is 4, and we divide it by the MR, or the RFM, whatever you want to call it, of copper sulfate, which is going to give you your moles. Okay, so I'll just plonk that through on here. So that's 4 divided by 159.5 gives me 0.025 moles. If you look at the question, you can see that it's a 1-to-1 ratio. So what we can say, if I've got this many moles of copper sulfate, I'm going to have the same of iron. So all we've got to do now is we've got to use the fact that mass is moles times RFM and do the 0.025 multiplied by the 56, which is the mass of iron, and that will give you your final answer of 1.4 grams. Okay, that is a hard calculation question because we've got basically kind of two things in one. We've got a reacting masses question here, and then up here we've got really just sort of getting you to think about moles and decimeters to try and work out how many would be in 50 centimeters cubed. I really don't think that is an easy question at all, okay, which is why I've obviously picked it and put it on this paper. So let's keep on going. Obviously I know we're going at quite a pace, but obviously the idea is this video you can pause it and pick up as you go. Right, question 5. This is not a hard question. So it says complete the diagram to show the arrangement of the outer shell electrons of hydrogen and chlorine. Well, what you should do is think, well, how many electrons does each one have? Hydrogen, it's got 1, chlorine's got 7. So I'm going to take the 1 from the hydrogen and put it there. And I'm going to take 1 from the chlorine and put it there. Try putting in the rest of my chlorine ones. If I can go around each atom and count either 2 or 8, they're happy. We've got 2, we've got 8, we're happy. Okay, so nice, easy question following on from the nightmare that was the last question, but the next one is difficult. Now, this is a 6-mark question on the difference between a weak and a strong acid. What we're going to do with this is we're going to come back to it once we've done the other questions. Okay, just because it's probably the one that's got the most planning, maybe not planning, but the most time we need to spend on it. So let's keep on going. Right, this is a nice easy question. So question 6, it just wants you to basically fill in the profile for this diagram. Now ideally you should have a ruler, but it doesn't really matter. So you're going to have a line here, and it's going to rise up for our activation energy, and then it's going to fall. But it does say that we need to label the activation energy. Okay, so there is my activation energy. I need to tell them where the reactants are, the products, and I need the overall energy change, which is this here. So 2 marks on offer, okay? You get 1 mark for basically saying this is the activation energy, and your other marks come from getting the reactants and the products in the right place. And obviously it's exothermic, so it needs to have reactants higher than products. It would be the other way around if it was an endothermic reaction. So a nice easy 2 marks there. Then we've got a classic bond energy calculation question. This is quite nice because they've already drawn out all the things for you. But you just need to be careful. So what I always do with this is I just sort of split me thing I've got there in 2. And then we've got the reactants. And we've got the products. So let's just quickly tot it up. On the left, this is where I'm obviously breaking my bonds. And on this side is where I'm making my bonds. And if you remember, bond breaking takes in energy. Bond making gives out energy. Okay. So we tot it up. On this side, we've got 1, 2, 3, 4 CH bonds. And we've got, well, there's 2 of these. So there's 1, 2 double oxygen bonds. On the other side, we've got 1, 2 carbon double oxygen bonds. And we've got, again, we've got to remember there's 2 of these. So we've got 1, 2, 3, 4 OH bonds. So we need to do that multiplication. So that's going to be 4 lots of 413 and 2 lots of 498. On this side, it's going to be 2 lots of 805 and 4 lots of 464. If you get a total on both sides, you'll find that this one is 2648. Okay, and this one over here is going to be 3466. In reality, this one over here is negative and this one is positive. So what happens when we sort of add them together? Essentially, you can just take away one from the next. So if you'd rather just do break, take, make, if you'd rather do it that way and not worry about the signs, you can just ignore them and go, right, well, it's going to be 2, 4, 2, 4, I can't read, 2648 minus 3466. Okay, which will give us a final answer of minus 818, which is correct because it's an overall exothermic reaction. So the marks here, there are 3 marks. It's basically 1 for getting your totals on each side right and 1 for getting the final answer correct. Moving on. Okay, so question 6 is about, and it's another big sort of 3-mark question about comparing 4 different powdered metals. So again, we're going to come back and we're going to do those ones last. What we're going to do is we're going to have a look at the very last question, which is question 6. So question 6 is sort of linked back to this 6-mark question that we've got here, but it's on a slightly different thing. So it says, we're investigating displacement reactions and we're looking into the relative reactivity of 4 different metals, which are W, X, Y, and Z. So here we've got the results and we've got to justify the order of reactivity. So we've got to find which one of these we think is most reactive, then which one we think goes in second place, and which one we think goes in third. And this is actually quite easy. So if you look at the table, anywhere you can see no change, I'm just going to put a little star. So anywhere it says no change, that means the metal hasn't reacted. We've put it in a solution of something and just nothing's happened. So looking at that, clearly the most reactive one must be W, because it's the only one that's reacted with 1, 2, 3 substances. So that one must go in first place. Now if you look at X and you look at Y, it's not immediately obvious which one of those yet goes in second place or third place, because they've both got 2 things. But we do know that metal Z must go in the second place. So what we've got to do is we've got to explain our answer. So I think explaining W is easy. W reacts with the most solutions. So that obviously means it's the most reactive. And then Z reacts with none of them, which obviously means it's the least reactive. Now in terms of explaining, trying to work out the order for Y and, for the X and the Y, well, I personally would put Y in second place and I would put X third. Now, if you look at the evidence, hopefully you can spot why I've said this, okay? So if you look at the first bit, they both get a brown layer formed on the metal, so that's no different. Here, they both don't react with magnesium sulfate, but metal X only gives us a few gas bubbles with sulfuric acid, whereas metal Y gives us lots. Or, you know, it doesn't say a few, it says gas bubbles. So that would indicate what we can say here. Y is more reactive than Z. Than X, as it produces more bubbles in sulfuric acid. And then finally, we've got this, sorry, I should have ticked that off. So that's 1 mark for getting the order correct and 1 mark for each of your explanations for that one there. And then last but not least, before we have a look at the 6 markers, so the student concluded that these results could also be used to justify the order of reactivity of copper, magnesium, hydrogen and zinc. And they say that the student is not completely correct. So you need to use the results in table 2 to explain why and suggest a further experiment that would provide evidence for the conclusion. So let's have a look back at the results, okay, and see if we can work out why they're a little bit wrong. So they're saying that copper, magnesium, hydrogen and zinc can be justified by these results here. So we can know which one the most reactive is, which one the least reactive is, etc. Okay? So the issue that we've got with this particular one, I suppose, is looking at we're kind of looking at things in a different way now. So we're now looking at copper, magnesium, hydrogen in sulfuric acid and zinc. So there's copper, there's our magnesium, it's H2SO4, so it's got hydrogen in it, and that one's got zinc in it. So now we're looking to see sort of how many of the metals they've reacted with. So what we can say here, and we're looking at the displacement. So what we can say here is that magnesium is the most reactive metal in the sense that it's not getting displaced by any of these other metals. So thinking back to your reactivity series, this magnesium here in the magnesium sulfate isn't getting kicked out because it's really reactive. Okay, and that would be something this student is right about. So we can say magnesium is the most reactive as none of the metals displace it. Okay, think back to where we had our couple. I think it was Mr. Copper and Mrs. Magnesium. Mr. Copper, and he got kicked out by Mr. Magnesium. Well, magnesium is a reactive metal, so it's not going to get displaced by much. And then we look at zinc. Okay, so zinc here, that's only displaced by one of them. So clearly, again, we can say that zinc is the next most reactive. As it displaces only one, it is displaced by only one metal. But if you look at copper and hydrogen, so this one and this one, you can see that they've both reacted with the same number of things. They've both reacted with 3 things. Yeah, so 1, 2, 3, 1, 2, 3. So it's very difficult for us to tell which one out of copper and hydrogen. So they both reacted with 3. So it's hard to tell the difference. So what we could do is and this is a hard mark, probably the hardest mark on the paper. If I added sulfuric acid to sulfuric acid and copper nitrate, what you would find is that the copper is less reactive than the hydrogen, okay? And that the copper would not react with it. So, bit of a weird one here in terms of that one, but if you added sulfuric acid to the copper, in theory, because copper should be less reactive than hydrogen, we should see a displacement reaction. We shouldn't see a displacement reaction. Okay, and that would let you work out which one out of the 2 substances was more reactive. So we'll go back and we'll have a look at those 6 markers now, although one of them I think is a bit trickier than the other one. So going back to this one here about weak and strong acids, and then the other one I think I'll probably just refer you to the mark scheme for, because it is quite straightforward in comparison to this one. So question 5, in my mind, is one of the harder questions that's been asked in recent years. Okay, so it says hydrochloric acid is a strong acid, ethanoic is weak. Describe a reaction that could be used to show the difference between a weak and a strong acid, and you should explain why the weak and the strong acid give different results. Okay, so this is hard because it's very specific. It says describe a reaction that could be used to show the differences between them. So how could we actually explain this in terms of our answers? Okay, so the first thing to know, and I know it says describe a reaction, but I would start off by saying that strong acids tend to have lower pHs. usually between, like, I don't know, 0 and about 3 or 4, okay? Whereas weak acids tend to have higher pHs, but obviously they're still below 7. So about 4 to 6 or something, okay? And that would actually get me a couple of marks, because clearly that is the main difference between strong acids and weak acids, is their lower pH and higher pH, okay? So what we could do is we could maybe react a strong acid with something and then react a weak acid with the same thing. And we could measure the pH of the overall solution. So what I would do is I would take a strong acid, maybe something like HCl, and add it to magnesium. Okay, so I'm going to take some strong acid and add it to my magnesium. Then I would measure the pH of the resulting solution and the time taken for the magnesium to dissolve. Okay, I could do the same for a weak acid. Okay, so maybe something like ethanoic acid, and compare the results. So we've got strong acid reacting with magnesium, and obviously maybe repeat it, and we do the same with a weak acid, and we're going to measure the pH and how long it takes. Now what I would expect is that the strong acid will give a higher pH solution, let me rephrase that, will give a faster rate of reaction and reach a lower pH. And the reason for this would be because strong acids are fully ionized, which means they will produce more H+ ions. Now the only other thing I could say here, and I meant to put it in the text, is that I would keep the concentrations the same, okay, of my acids, because obviously it wouldn't be a fair test otherwise, would it, if I use one concentration of this acid and one concentration of this one. So if I was looking at this and I was marking this, there's 2 marks there just literally for saying what kind of pHs acids, strong acids and weak ones tend to have. But then the rest of it, you're going to get a mark somewhere. If you've mentioned about full or partial ionization, that's going to get you a mark. But the rest of it comes from actually just, the simplest thing to do is to take an acid, react it with a known amount of metal, and do the same with a weak acid, and then compare your results on the pH and the time taken to dissolve. And obviously all of that in there together will get you 6 marks. And maybe if I'm being a bit picky, I should have specified the amounts and concentrations, but I'm just thinking about time because I don't want the video file to be absolutely massive. Right, last but not least then, we've got this question, and this one is actually quite straightforward. So what I'm going to refer you to do for this one is, if you have a look at the mark scheme on 6.3, have a look at the indicative content box. I'll talk you through what the logic is of this one now, but you can have a look and see, plan in your own answer. So it says the student wants to investigate the reactivity of 4 metals. And we've got a little diagram here. So there's our 4 different powdered metals, and we've got some dilute sulfuric acid. So it says, outline a plan they could use to investigate the relative reactivity of the 4 metals W, X, Y, and Z. The plan should account for the fact that all 4 metals react exothermically with dilute sulfuric acid. So what this should be getting you to think is, the more reactive something is, the bigger a temperature change we're going to have. So you need to plan what we could do with this sulfuric acid and a thermometer and any other equipment that you might use. If we added it to some of metals W, X, Y, and Z, what might we, if we want to work out which one the most reactive one is, what's that going to mean in terms of the results? And what apparatus would you use? And also, how would you use it safely? So if you're not sure, have a look at the indicative content, which is basically a load of bullet points, things that you could mention in your answer here. And a level 3 answer is going to tie those together to produce a method that obviously is appropriate. So, I hope that was useful, folks. Apologies, you've got the phone balanced on top of a bloody box, but the clip for holding up the webcam just won't fit my phone in it, and the webcam doesn't record it in enough visual detail. So I hope that was useful for you. What I might do if these don't upload to Teams is I might put them on YouTube instead, and you can watch them on there. Okay, so cheers for that, folks. All the best. Have a good one.